Welcome back to analog electronic circuits. This is lecture 32 and today we are going to continue from where we left off in the last class. We are going to talk about compensation. So, the topic is called compensation. However, it is just what we were doing. I did not really tell you that the topic is called compensation in the last class. In the last class, we were still working on a diversion. Right. In the last class, we just showed that the ratio of omega 2 and omega 1 in a two pole system, if suppose you forget about the existence of the zeros and so on and so forth, suppose you have a strict two pole system, forget about the third, fourth other poles if they exist, forget about them. Okay. Now, if you have a strict two pole system and you plan to use this two pole system within a feedback loop, okay, then you require some phase margin. All right. And depending on the phase margin that you require, you need a certain ratio between the two poles. So, if the two poles are at omega 2 and omega 1, then we showed that omega 2 by omega 1 has to be some large number, right, and you can arrive at that large number by solving a certain quadratic, right, lambda squared plus lambda times something which was a function of the phase margin as well as the gain, the open loop gain, okay, A naught as well as the phase margin plus 1, right. You can solve this quadratic and you will arrive at the ratio of the two poles. Now, this particular ratio of the two poles has to be large, right, and this pre knowledge helps us to easily solve the quadratic. Instead of solving the quadratic, we can just say that middle term, 1 by of that middle term is nothing but the ratio of the two frequencies. All right, this is what we had done in the last class, right. Now, a continuation of the same. So, this particular topic is now going to be called compensation. When you manage to engineer the two poles to be a certain ratio that you want, that engineering, that exercise is called compensation. Okay. So, let us see. Suppose you know, the boss has said that give me a design with a phase margin of phi when the open loop gain is A naught, right. Automatically you plug in your numbers into yesterday's equation, in the last class's equation, and you find that the ratio of the two poles has to be a certain number. You arrive at this number and keep it in the stack, right, maybe 1500 something. We had done some crude computation, we did not really do it accurately, we just plugged in some numbers, we got a number like 1500. We said let us say the gain is 1000 and let us say the phase margin required is 60 degrees, roughly 1500 was what came out. Okay. Now, you look at your system, all right. What is our system? As an example, so we were looking at two different circuits, one was the cascade amplifier, the other was the cascode amplifier. So, actually we have discussed the cascade substantially in the last class, but I will do it again all over again. Let us discuss the cascode, because we have not really discussed it that much. So, as far as you remember, the cascode circuit, I am just drawing the small signal equivalent. We are going to assume that this resistance is so large that it does not really matter. Okay. So, let us say it is not really in the picture. Invariably what you are going to do is, instead of that resistance, it is going to be another cascode with PMOSes, right. So, it is just going to double up, all right. So, this is our cascode, and over here when we did our analysis we had placed some capacitors. So, first of all this is GM1, this is GM2, and then we had placed some capacitors C12 between 1 and 2, and then there was C2, and then there was C3. Yeah, this is all that was there. Okay. This is what was there, and each of these devices GM1 also has RDS1 and GM2 also has RDS2. This was our system that we had analyzed earlier, and when we did the analysis we found that the system has some zeros, and the zeros are going to be computed straight from the short circuit transconductance. Okay. This system has a couple of poles, and the poles are going to be computed straight from the output impedance. All right. Then we had done an analysis of the output impedance of the circuit, and doing the analysis of the output impedance is not very hard, because this is going to be at ground. So, C2 and C12 will appear together, and then it is just an application of one of our old formulae. Okay. Looking in from the output, you see the impedance at the source of MOSFET number 2 times the intrinsic gain of MOSFET number 2 plus the impedance at the source of MOSFET number 2 plus RDS2. Okay. This whole thing appears in parallel with C3, right. So, you do all of this computation, it is not a very difficult computation. Okay. And then we arrived at an expression, and I am not going to do the computation again, because we have already done it. I am just going to write the denominator polynomial that we arrived at, and the denominator polynomial that we arrived at purely based on the output impedance calculation looked like this. So, it was 1 plus S times something plus S squared times something. All right. So, this is what it was. There is something in the numerator which we are not interested in right now. Okay. Right now, we are going to forget about the numerator. We are just going to assume that it is a plain vanilla 2 pole system, and we are going to learn how to deal with these 2 poles. Okay. In fact, invariably what is going to happen is that the zeros are going to be at much higher frequencies than the poles. If the system had to go unstable, it would go unstable even before the frequency hits the 0 frequencies. Okay. So, let us not worry about the zeros for now. We will also learn how to tackle the zeros a little later. Okay. Sometimes the zeros are going to be the right half plane zeros are going to pose as problems, right. So, we are going to learn how to tackle them separately, right, that is a separate exercise. For now, forget about the zeros. Now, in this situation, we have to make sure that the ratio of the two poles is the set number that we had arrived at before based on the Boss's specifications. Okay. Now, if that is the case, if the ratio of the two poles is indeed so large, then how will you be able to factorize this denominator polynomial, right. This denominator polynomial is nothing but 1 plus s by omega 1 times 1 plus s by omega 2, or in other words it is nothing but 1 plus s times 1 by omega 1 plus 1 by omega 2 plus s squared by omega 1 omega 2. Okay, this is what it was. This is the denominator polynomial. Now, if this is the denominator polynomial and I am telling you in advance that omega 2 and omega 1, omega 2 is much larger than omega 1, okay, larger than omega 1 by a factor that we have computed of the order of 1000. All right. In such a scenario, what can you tell about this polynomial, or what can you tell about omega 1 and omega 2? You can see that omega 1 is going to be 1 by omega 1 is just going to be this coefficient, because 1 by omega 2 is much smaller than 1 by omega 1, right. So, we know in advance the value of the ratio, right. You can see for yourself that this value of the ratio is some large quantity. If it is not large, then you are probably doing something wrong, right, or you are probably dealing with a phase margin that is not sufficient, correct. So, immediately you can tell that 1 by omega 2 is not really a concern, in which case 1 by omega 1 is nothing but what you have got in coefficient number 2. Done, right. So, we do not really know how to factorize this analytically, but we know how to factorize this, how to arrive at the two poles by inspection looking at the quadratic equation, right. So, my 1 by omega 1 is nothing but what I have got, and if I know 1 by omega 1, then 1 by omega 2 is a no brainer, because the product of omega 1 and omega 2 is 1 by of the third coefficient. Okay. So, omega 2 is also a no brainer, and then you have to set omega 2 by omega 1 equal to whatever that gigantic number you had. So, let us just work it out over here. Let us do the algebra. Omega 1 over here is, so 1 by omega 1 is so much, okay. Omega 1 omega 2 is 1 by of this, which means omega 2 this is 1 by omega 1 omega 2, sorry, this is omega 2 times omega 1, omega 2 times omega 1 times 1 by omega 1. So, this happens to be your omega 2, and 1 by omega 1 is just the numerator part of this, which means that omega 2 by omega 1 is nothing but the square of the numerator part. Fine, this is what it is. All right. So, omega 2 by omega 1 is so much C 1 2 plus C 2 plus C 3 times R d s 1 plus C 3 R d s 2 plus times 1 plus G m 2 R d s 1, the whole squared, right, this whole thing squared divided by whatever you have in this expression. Fine. Now, this ratio has to be set to a certain predetermined constant, a large number. How will you do the engineering over here? What will you tweak that will get you the maximum benefit? Which one of these will you tweak to get the maximum mileage? If you look at it carefully, first of all, you are not allowed to tweak the values of GM1, GM2, RDS1, RDS2, because this is what gives you the DC gain. Okay, the DC gain is all important. If you change the DC gain, then guess what, your set value is no longer set, right, that also changes, right, that is a function of A naught, that set value. Okay. So, you can't now tamper with the DC gain, the DC gain is fixed, right, that means GM1, GM2, RDS1, RDS2 you are not going to touch. The only things that you are allowed to touch are C12, C2 and C3, right, and by touching what I mean is that you can increase these values, you can't really decrease the values, okay, because the MOSFET is coming with a certain amount of parasitic capacitance C12, C2, C3 depend on that. You can't really dial those parasitics down, right, beyond a certain point. I am sure you would have already dialed it down as far as possible, right. You can't dial it down any further, right, and now your only option is to increase these capacitor values. Now, if I allow you to increase the values of C12, C2 and C3, which one will you work with to give you the maximum value for money? Look at your expression carefully, right. If you look at your expression carefully, you will see that the maximum value for money is going to come from C3, and the reason why the value for money is going to come is because it is attached to a factor which is large. Okay. So, C3 is attached to a factor that is large. Therefore, a slight increase in C3, remember C3 is there in the denominator also. Okay. So, if you take C3 common from the numerator you get C3 squared, in the denominator you have only C3, right. So, it is going to be roughly proportional to C3, all right. So, C3 over here is the dominant capacitor, all these terms have C3 in them. C12 and C2 can be held to be small compared to C3, you add extra C3 on top, right, from the outside you add extra C3, and therefore, C12, C2 are all parasitic capacitances. If you ignore them, then the numerator term is proportional to C3 squared, the denominator is proportional to C3, which means overall this ratio is proportional to C3, which means you increase C3, you can increase the value of the ratio that you desire. Fine. So, this is going to be the compensation technique. The compensation technique is going to be to add capacitance out here, right, at the load. at the load we just dial in more and more and more capacitance till the requirement of phase margin is met, is satisfied. All right. So, this cascode amplifier requires extra load capacitance, and this is the way you are going to compensate it. This kind of compensation is called dominant pole compensation. Okay. So, this particular style of compensation where I add extra capacitance at the load, it happens to be called dominant pole compensation, although all compensation is dominant pole compensation, right. There are some techniques where you add a 0, we are not going to discuss those in this course, it is out of bounds, right. All the other pole type compensation techniques are dominant pole compensation. However, in circuits this specific way of adding extra load capacitance till your phase margin requirement is met, this is called dominant pole compensation. So, C3 is the load, right. You can add as much load capacitance as you want outside the chip, outside the circuit, and that is called dominant pole compensation, that will meet the requirements of phase margin, and now you can use your amplifier in a feedback loop. Fine. All right. So, this is the cascode circuit. Now, let us look at the cascaded circuit. The cascaded circuit we had actually half discussed, right. I do not know how far you followed, but we will do it again. So, as far as my notes are going, when we discussed the cascaded amplifier, this is what we did, and my labels seem to be as follows. I called this as C12, and this was called as C2, this was called C23, and this was called C3. R1, R2, and my devices had GM1, RDS1, GM2, RDS2. This was the circuit that we had analyzed. All right. And in this particular circuit, we did not really write out the complete analysis, right. I said that the complete analysis will take a lot of time, and it is not really worth the while. However, I am just going to write out the expressions, right. As far as you should remember that this particular circuit had two right half plane zeros, and the zeros came explicitly from the short circuit current analysis, short circuit transconductance analysis. You do the short circuit transconductance analysis, you will get the zeros. Then the poles had nothing to do with the short circuit analysis, the poles had everything to do with the output impedance. So, if I look at the output impedance, I will arrive at a 2 pole, a second order denominator polynomial, and the denominator polynomial looked like this. Okay. So, what I am going to do is I am going to make one simplification. I am going to lump RDS1 into R1 just so that my expression is simpler. I am going to lump RDS2 into R2. So, R2 is the old R2 in shunt with RDS2, R1 is the old R1 in shunt with RDS1. Okay. Let us just put that in over there, and then I am going to write out the denominator polynomial. The denominator polynomial looks like this, it is 1 plus s times plus s squared times. Okay. And let us start with the s. Okay. So, that is the s term, and the s squared term looked like this. All right. So, this was my gigantic expression, and in this R1 is the old R1 in shunt with RDS1, R2 is the old R2 in shunt with RDS2. So, this is implicit. All right. Now, once again your boss asked for a certain phase margin and a certain gain, open loop gain and a certain phase margin. Okay. The open loop gain is nothing but GM1 times R1 times GM2 times R2, and it is set. Okay. You are not going to tamper with GM1, GM2, R1 and R2. These are fixed quantities, right, they based on your DC design. Now, based on this value of A naught, you arrive at, and based on the phase margin that you need, you arrive at a certain ratio of omega 1 and omega 2. Omega 2 by omega 1 has to be some large number, which is a function of A naught and phi, the phase margin. Okay. Now, after arriving at this large number, you are going to say that therefore, my denominator polynomial that I have, this is the exact expression, by the way. This does not include any of the Miller's approximation and so on and so forth. This is the exact expression. You just take the output impedance, find out, work out the output impedance of this circuit. Okay, precise expression. There is nothing in this, no hand waving. All right. And in this expression, therefore, right, one possibility would be to factorize this somehow using your quadratic solutions, right, minus b plus minus square root of b squared minus 4ac by 2a. You can do all of that, but doing all of that is not going to be worth your time. Okay. Much easier understanding would be that omega 2 by omega 1 is already a large number, which basically means that if my denominator polynomial looked like this. If this was my denominator polynomial, then this would look like 1 plus s into 1 by omega 1 plus 1 by omega 2 plus s squared by omega 1 omega 2. I am doing this repeatedly so that you get the hang of it, right. Some of you will find this boring because it is the same thing that I am repeating over and over again, but this is the way you learn through repetition. So, over here 1 by omega 1 and 1 by omega 2, the sum of these two is this particular term, the middle term, okay. And omega 2 by omega 1 is a very large number, which means that 1 by omega 2 is small compared to 1 by omega 1. The reason why is because omega 2 is much larger than omega 1. Omega 2 much larger than omega 1 means that the second term 1 by omega 2 term is very small. So, you ignore it. As soon as you ignore it, immediately you know the value of 1 by omega 1. So, the value of 1 by omega 1 is nothing but the first term, sorry, the second coefficient, right. And as soon as you know 1 by omega 1, omega 2 is also not very hard to find out, because the product of omega 1 and omega 2 is 1 by of the second term. All right. So, this is the plan. Now, we are going to execute the plan and we are going to find out the ratio of omega 2 and omega 1. So, omega 2 by omega 1, sorry, omega 1 omega 2 is 1 by of this, right. So, omega 2 is 1 by of this times omega 1 by omega 1. So, this is omega 1 omega 2, but I am not interested in omega 1 omega 2, I am interested in omega 2. Omega 2 is omega 1 omega 2 times 1 by omega 1, and 1 by omega 1 is nothing but this second coefficient. Okay, so, this is omega 2. We are not even interested in omega 2. We want to find out omega 2 by omega 1, which is nothing but omega 2 times 1 by omega 1. Fine. So, an expression similar to what we had found for the cascode. So, in the cascode we had found an expression that looked like this, okay. And in the cascade we have found an expression which is similar, some square divided by something else. Okay. Now, what do you want to do with this? what would you want to do with this? This has to be equated to some large number. Okay. Just by the way, we had also done the Miller's approximation, right. What result does that give? Does that also give something similar? Because this is the time to do it, right. This is the junction in time when you should also think of the Miller's approximation. When we did the Miller's approximation, what we thought of was that at the first pole, at the lower pole frequency, C23 can be broken up as C23 times C23 times 1 plus GM2R2 over here. So, this was Miller, okay. And therefore, as far as my first pole is concerned, as far as omega 1 is concerned, omega 1 is less than omega 2, as far as omega 1 is concerned, 1 by omega 1 would be equal to R 1 times C 1 2 plus C 2 plus C 2 3 times 1 plus G M 2 R 2. Now, we also found some omega 1, right. 1 by omega 1 for us was this middle coefficient. How far are we from, I mean, between Miller and this Miller coefficient, this middle coefficient, what is the difference? So, I have got R 1 C 1 2, I have got R 1 C 2, okay. This term is not there over here, C 2 3 times R 1 does not really show up over here, but I have got C 2 3 times R 1 is also C 2 3 times R 1 times G M 2 times R 2 is over here. So, this particular one, okay. And then C 2 3 times R 1 is also over here, okay. So, all of these terms are matching. This stuff is just a little bit that is missing. From the actual value of 1 by omega 1 that I estimated with Miller. Now, when I did the Miller estimation, right, you can immediately see that this GM2 R2 times C23 times R1 is the largest term. The same thing is there over here, right. So, if you really think about it, these other things are not that important. Okay. This little inefficiency of Miller is not that important, you can keep it aside. Okay. Yes, this is the accurate version, but the Miller version is giving you very close to the actual result, it is very close. All right. Now, this is 1 by omega 1. When we did Miller, we also had to do, we also did in a different way, we found out the second pole, right. The second pole was not so straightforward. When we talked about the second pole, we said that all these capacitors are now going to behave as short circuits, and there is going to be some ratio of C23 and C2, C12 plus C2, that voltage is going to appear here, and that is going to pull some current through the MOSFET. So, you are actually going to see an effect of GM2 coming into the second pole. All right. So, this is what we had suggested. So, Okay. So, this value of 1 by omega 1 is actually very close, right. This is the only discrepancy. Between Miller and the exact expression. Okay. Now, let us try to find out the value of omega 2, right. So, when we worked out omega 2 with Miller, when we worked it out with Miller, we said C 23 is a short circuit, C 2 plus C 12 is also a short circuit. Okay. So, now we forget about this. Okay. This was only for the forward direction. Okay. When these are all short circuits, R 1 is not very interesting anymore. R 1, RDS 1, all of these go away. Okay. GM 1 is anyway dead, it is not relevant. So, if I apply a voltage V over here, then the voltage over here is going to be V times C 23 divided by C 23 plus C 2 plus C 12. It is a voltage division between capacitors. Okay. What I have written is C 23 plus C 2 plus C 12, that is the voltage up here. Now, if that is the voltage up here, then GM times that voltage is drawn through the MOSFET, and when I draw GM times that voltage, okay, when I draw that much current, then that adds on to the output conductance. So, the output conductance is therefore so this is only for the second pole calculation, not anything else. So, only for the second pole calculation, the output conductance is GM2 times, yeah, okay, as far as this MOSFET is concerned. Plus we have the series path between C 23 and C 2 C 12, right. This path is also there. So, that is also going to create output conductance, or in other words, this voltage is V, this voltage is so much V times C 23, there is going to be some current through this capacitor also. Okay. So, okay, series combination of C 23 and C 2 plus C 12. Then there is current through R 2 and there is current through C 3. Or in other words, I have got a capacitor of value C 3 plus C 23 into C 2 plus C 12 by C 23 plus C 12 plus C 2. This is the capacitor, and I have got a resistor of value R 2 in shunt with Okay. So much, and therefore, 1 by omega 2 is this R c time constant. We are just trying to compute 1 by omega 2, omega 2. The pole frequency, as far as the pole is concerned, you are looking at one resistance, which is the parallel combination of R 2 and this, and one capacitance, which is a shunt combination of C 3 and this. Okay. So, the pole frequency is just 1 by R c. 1 by the pole frequency is just R c. Fine. So, in other words, 1 by omega 2 that we got using this technique would be the product of these two. Okay. Now, to do the product of these two, I think it would be better to combine these two parallel quantities R 2 and so much. Okay. Okay. Then you have to multiply the C with the R. So, this is a big multiplication. The first thing that you are going to do is you are going to multiply by C 23 GM 2 numerator denominator. Okay. The next thing you are going to do is you are going to cancel out this factor. Okay. So, you have to cancel these two out and multiply it over here. Fine. That will leave you with a gigantic result. The result is going to be fine. So, this would be the result of our so called shortcut analysis, the analysis which did not require the actual calculation of the output impedance, right. I mean this particular expression was something that I wrote from our actual calculation, very hard work, right. This particular full fledged expression was something that we wrote from hard work, correct. But this expression is something that you can arrive at much faster, right. If you know the values of these individual capacitors, then this particular expression is going to come out much faster, do not worry about it. Okay. And in such a scenario, what is the difference between our original accurate expression and the expression that we have got now? So, 1 by omega 2 that we have computed accurately is actually this blue denominator 1 by omega 2 is the blue denominator divided by what is inside the square, the numerator part that is inside the square. Okay. So, the blue denominator divided by the numerator part inside the square, that is the accurate value of 1 by omega 2. So, 1 by omega 2 accurate, let me write it down. So, this is the calculation from our quick analysis, and this is the accurate expression. I think we have made a mistake. The dimensions are not right in the red one. Red one, the numerator polynomial is c squared, actually c cube, r and gm is nothing. So, it is c cube divided by c. So, this is coming out to be c squared. So, that is wrong, it should be time. 1 by omega 2 should look like r times c, not c squared. So, let us check. So, if dimensions are wrong, you immediately stop. Okay. So, we checked our dimensions over here, they are not correct, we go back. Where did we make the mistake? We had found y out was GM2 times ratio of two capacitors, fine, plus S times capacitor, which is fine, plus G2, fine, S times C3, this was fine. From here I took out the capacitor portions, C3 plus C23, C2 plus C12 divided by this. This is one capacitor, right, this is the capacitor, and the resistor is R2 in parallel with GM2 C23 by C23 C12 plus C2. R2 in parallel with GM2 C23 and in the numerator C23 C12 C2. Okay. So, resistor product divided by resistor sum. And then we multiplied numerator denominator by C23 GM2, this should not have come. Okay. So, that is the mistake we made, there is an extra C23 GM2 over there. Okay, C23 GM2 just cancelled out, we wrote it all over again. So, C23 GM2, yeah, this is now correct. Fine. Okay. So, now it is RCC by C, which is RC. Okay, great. Now, let me just write this down. So, from the accurate expression I was writing out 1 by omega 2, and over here we are going to have okay. So, this is what it is, all right. Now, what you are going to see is that in this denominator expression, in this 1 by omega 2 expression, once again C3 C23 matches, C3 C12 matches, C2 C3 matches, C2 C23 matches, C12 C23 matches, R2 matches, but there is an extra R1 in the accurate expression. Okay. All right. So, you can think of multiplying this by an R1 and multiplying the denominator also by an R1, just so that the numerator now completely matches up. Now, if we look at the denominator, I have got C23 GM2 R2 times R1, which is matching. Then I have got C2 R1, C23 R1, C12 R1. So, this entire term is matching, this entire term is matching. The only term that is left out is what I had over here. Okay. So, there is a slight discrepancy, right. It is the same discrepancy. Even as far as 1 by omega 1 was concerned, we had a little discrepancy over here. 1 by omega 2, we have the same discrepancy over here. Otherwise, they look pretty much the same, whether you do the exact analysis or you use the Miller's approximation, right, you get more or less the same result. Okay. So, then what do you do once you have this ready? What do you do? Supposing you work with any one of these two expressions, right, omega 2 by omega 1 is over here. What are you going to do as far as engineering is concerned? You can't touch GM2 R1 R2 GM1, these are not things that you can touch. You can only touch the capacitors, and if you look at the capacitors, the one that is going to give you maximum value is this term, because it has a multiplication with a large number and it is coming inside a whole square. Okay. If you look at it very carefully, omega 2, if I increase the value of frequency of C23, then omega 2 is actually going to decrease, omega 1 is going to increase. I am sorry, 1 by omega 2 is going to decrease, which means that omega 2 is actually going to increase, omega 1 is going to 1 by omega 1 is going to decrease, I am sorry, 1 by omega 1 is going to increase, omega 1 is going to decrease. In other words, when I tamper with C23, this was my two pole system omega 1 omega 2, omega 1 is going to decrease in frequency, omega 2 is going to increase in frequency, and the net effect is going to be that the ratio of omega 2 and omega 1 is going to be managed. All right. So, this is where we are going to stop for today. We have been talking this exercise, this entire engineering exercise is called compensation, right. So, we tried to do two different circuits, the cascode as well as the cascaded amplifiers, and in the next class we are going to try to incorporate all of these. Thank you.